So let us continue our renewable sources of energy session here. So the next kind of energy we have here is fuel cell. So what is a fuel cell? What is a fuel cell? Fuel cell is a electrochemical device. So what does it do? What does a fuel cell do? So it consume energy. This electrochemical device, that is fuel cell, consumes not energy, consumes a fuel and convert this fuel into electricity. So this is very much similar to a battery. So if we compare fuel cell and a battery, the working is very much similar, but the major difference is that in this fuel cell we have continuous supply of fuel, and in battery you have discontinuous supply. That is, it has chemicals stored inside. So battery has stored chemicals which react and produce electricity. So for the stationary fuel cell power systems which are developed for commercial power generation, the major fuel that is used here is hydrogen. So these hydrogen fuels are hydrogen fuel, I would say, is input to produce electricity. So applications, different fuels may take place in the form of different chemical processes in electricity generation. So a typical fuel cell, that is hydrogen fuel cell, can be seen here. So we have hydrogen that is going in here, and electrons, hydrogen is here, we have, it is split into ions, the ionization happens here, and electrons are going through. We have oxygen, air going in here, water and air is going in here, and unused gases go out. So this flow of electrons here generates electricity. So we have anode, cathode, and this electrolyte here. In this case, this continuous supply is there. This is the major property of fuel cell, continuous supply. The phenomena is very much similar to battery, but this is a continuous supply. So the kind of reaction that is happening here is, at anode side, the reaction is this hydrogen is being split into hydrogen ions, H plus electrons. So this is 2 into 2, I would balance this reaction 4 and 4 electrons. Then we have cathode. So at cathode what is happening, this oxygen is reacting with our hydrogen ions, that is this thing, plus electrons to produce water, which is, this water is made to go out here. So, in this case also we have 4 and 4. So, net reaction becomes the hydrogen plus oxygen is producing water. So, this is combining these two reactions. So, this is how electrons are being produced here and electricity is generated. So, another source in place of hydrogen may be natural gas. So, in current stage of fuel cell application, there is a limitation of hydrogen production. Now, hydrogen production has limitation. Hydrogen production is an issue. So, this is limited, as well as cost is high in this case. So, stationary fuel cell power systems are available in the market, which are primarily built for natural gas fuel. So, natural gas is mainly composed of methane, which is the major component in natural gas. So, in this case, the power system leads to generation of carbon dioxide. The reaction becomes CH4 methane plus water generates carbon dioxide plus H2. So, this is directly I am putting the net reaction here. So, we can see that we have carbon dioxide as an output here. So, a trade off has to be made that we are using a kind of renewable energy or a kind of fuel cell which is a renewable energy, but these resources are being used here, and carbon dioxide, which is a greenhouse gas. It's a greenhouse gases is produced. So, if natural gas based fuel cell power system is to be used for energy supply for a manufacturing system or for a big concern, a quantitative trade off analysis must be conductive. I would better here write quantitative trade off analysis, that is the impact on both the sides, that is the use of impact, use of a natural resource, then emissions of carbon dioxide, that is carbon footprint. So, these must be evaluated against the energy efficiency, that is the energy output only. So, net environment emission savings of using the fuel cell power system over local grid electricity, that is the local grid electricity might be thermal power plant, if hydro power plant is there, then it is good. So, it has to be compared with this one. So, in such case, the life cycle emissions of the fuel cell power system must be considered in this trade off analysis. So, this must be considered to assess the effect of environmental emission mitigations. So, next kind of energy I have is geothermal energy. So, what is geothermal energy? How do we utilize this one are the question. What is and How? So geothermal energy is the heat from the earth. Uh, Geothermal energy is the heat from the earth. So it is also a clean and sustainable kind of energy. The resources of geothermal energy ranges from the shallow ground, hot water, then maybe hot rock if it is found at some distance beneath the earth, if it is found at some distance and this distance is beneath the ground surface, or I would write earth surface. So these can be the sources of geothermal energy here. So this difference in temperature is utilized to generate electricity. So even down deeper to extremely high temperatures of molten rock, for example, I would even write molten rocks or magma, these can also be utilized. So almost everywhere the shallow ground or the upper 3 meters of earth surface, 3 meters is about 10 feet, maintains a nearly constant temperature. For example, if I say this is my earth surface and this is 3 meters height, then this temperature here is about 10 to 10 degree to 16 degrees centigrades, which is equivalent to 50 to 60 degree Fahrenheit. So this temperature is always there. So most power plants need steam to generate electricity. The steam rotates a turbine that activates a generator which produces electricity. Many power plants still use fossil fuels to boil water for steam. So geothermal power plants, what they do? They use steam produced from reservoirs of hot water that those are found a couple of miles and more below the earth surface. So when we go below, the temperature is higher at certain places. So this difference, this hot water found at a few kilometers below the earth surface is used to produce steam. So there are three kinds of power plant that use geothermal energy. So this is a kind of a power plant. The cold water is pumped down and steam and hot water is coming up. So this difference is used to generate electricity here and it is being transported to the grid. So the transportation is happening here. So this cycle is being running. So this cycle is running continuously here. So the main issue here is building this setup to take our connection to the this much depth. So this is, I say, if it is maybe 5 kilometers. So there are three kinds of geothermal power plants. Number one, dry steam geothermal power plant. Number two, flash steam geothermal power plant. Number three is binary cycle Now dry stream power plants draw from the underground resources of steam. The steam is piped directly from the underground wells to the power plant. So where it is directed into a turbine and generator unit. So this dry, flash and binary cycle geothermal plants have different kind of mechanisms of use. Number one, dry geothermal plant. So the dry stream geothermal plants draw steam from the underground resources. Steam from underground resources. The steam is actually directly made to pass through the pipes for underground wells. So we have underground wells here. So these are the wells, this is ground surface. This here we steam is made to pass through pipes. Under here we have pipes going through here and steam is made to pass through here. So this steam is made to pass through these underground wells to the power plant where it is directed to turbine. So we have the power plant here and a generator or turbine is here with its fins, and the steam is made to fall into this turbine, and this one turbine is rotating this shaft and we have generated electricity. So as the steam flows upward, the pressure decreases and some of the hot water boils into steam. The steam is then separated from the water and used to power the turbine generator. Now leftover water is here condensed. Now next I have here is my flash steam power plants. So these have similar phenomena, but it use, because see the name here is flash, so it uses steam that is there in water. So they use the geothermal reservoirs of water with temperatures maybe of the order of 200 degrees centigrades. So this hot water flows upward under its own pressure, and when it flows upward the pressure decreases and some of the water boils into steam. So this water, we have water here, the water reservoirs, at some places we have high temperatures here. So this high temperature made the water to flow up in form of steam. So this steam is captured here, we have steam here. The steam is captured here and it is made to flow to our power plant. So this is, again we have the similar kind of arrangement here, the turbine is being run by this steam and steam is electricity is generated. So any leftover water or condensed steam here are injected back into the reservoir here. So any leftover water is injected back. So another is third one, binary cycle. Now these operate on water at low temperatures. So here the temperature is less, that is the other temperature was, this was of the order of 200 degree centigrade. If we say specifically in US they say it 182 degree centigrades. So in this case the temperature is less than 182 degrees. So these plants use the heat from hot water to boil a working fluid. And usually an organic compound with low boiling point. So, this working fluid, that is an organic compound, is then vaporized in a heat exchanger to turn a turbine. So, the water is then injected back to the ground, that is reheated. So, this cycles is made to run again and again. So, there are no air emissions or very little air emissions in this case. So, this is similar to this process flash, but the difference is that in place of taking this steam directly to the reservoir, this steam is used to heat a fluid here. This fluid is, this is an organic compound generally. Now, this fluid is heated and is then made to the turbine to generate electricity. For generating electricity. So, this is the only difference from the flash steam process. So, next I have is biomass energy. So, what is biomass? Biomass is an organic material. Biomass is an organic material that comes from plants and animals, plants and from animals. So, you might have heard of the term photosynthesis. What is photosynthesis? Plants absorb the energy of sun, and this process is called photosynthesis. This energy of sun is again then turned into the biomass, which is used as an renewable source of energy here, this biomass. So, when biomass is burnt, this chemical energy in biomass is released as heat. So, this photosynthesis, actually this is sun that stores energy in plants. So, when this is burned, chemical energy is released as heat, which can be used. So, this is used to generate electricity. So, this biomass can be either burned directly but this creates smoke, or it can be converted into biofuels. If you could recall, we had an energy ladder in which we had the biomass here, and here we had the advanced fuels, that is petroleum, etc. So, this was actually if we burn this directly, if here this was the condition, if burnt directly. So, some examples of biomass and their uses of energy are wood and wood processing waste. I can even write it here, wood and wood processing waste. Then these are burned to heat buildings, to produce process heat in industry and to generate electricity. Then we have agricultural crops and waste materials. Then these are burned as fueled or they are converted to liquid biofuels. They are converted to biofuels. Then along with this we have food or wood waste in garbage. Also we have animal manure. So this animal manure or maybe human sewage. So these are also converted into biogas. These are converted into biogas which can be burned as a fuel. So in this case food, wood waste, garbage, these are also burned to generate electricity in power plants, or they are also converted into biomass, biogas here. So I have a kind of electricity generation plant in which we have these biomass materials as input. So in this case this electricity is produced and is being supplied to the grids here. The biomass here is the pulp paper, lumber, plywood, cotton, anything can be used. And from animal sides also we have animal residues here, dung, etc. So here also we have process residuals. So this fiber can be used to make materials, then consumers use that, then food products also the consumers could use here. And even when the consumers use, the waste is produced, the waste that is you can be used as biomass. The solid waste, the municipal corporation can segregate the waste into the categories. The waste that can be used as biomass, that is from construction, demolition wood, yard trimmings, non recyclable organic compounds here, they can be used. So this decomposition and combustion can be done to have electricity, which can be again used by the consumers here. So this is a kind of a biomass cycle here. Biomass can be used in this way. So next, as I have discussed certain kinds of renewable sources of energy, it is cost benefit analysis. So to conduct the cost benefit analysis, various models are available to know the pollution reduction, to have the trade off between the cost and benefit, and to have the relation between the various efficiency levels and for all kinds of energy here. So one of the model here is developed by Yuan in 2013, which can be applied to all kinds of clean energy. In this model we have RI. So this model takes into consideration the emission factor. This is actually we have emission factor that is of pollutant from local grid power supply. Another factor it takes into account is the life cycle emission. Life cycle emission of what? Of the pollutant. If I say one pollutant, a pollutant I, this pollutant I may be carbon dioxide, this may be some other air emissions. So if I say pollutant I here, this may be carbon dioxide, sulfur, phosphorus or other pollutant emissions. So in certain cases, if I say life cycle emission of pollutant, the same I from the clean energy, right? So in this case, for example, in certain clean energy cases, this pollutant might even be zero. So here we have the difference of these two factors. If I say this factor is E for I pollutant, emission for I pollutant from local grid, and this is emission of I pollutant from my clean energy. Here J is my clean energy. So this is kilograms of carbon dioxide that is produced per kilowatt hour. If I say carbon dioxide, the pollutant that is chosen here, or this is again kilogram of the pollutant per kilowatt hour. These are the units here. So this difference EI local minus EI of my clean technology is a factor here. So this factor also involves total installed capacity of clean energy. Now this total installed capacity is again multiplied here. I will put it AJ, installed capacity AJ, clean energy system here, the system J. Now I have TJ here as well. TJ is operational lifetime of clean power system. Here this operational lifetime, I can put some unit maybe in hours, in minutes, whatever like. So this is also a multiplicative factor here. So this Ri is proportional to, that is, what is Ri, that is also needed to define here. I is the emission reduction of pollutant. That may be pollutant, this pollutant I, which the units may be kilograms per rupees 1 lakh, maybe these are the units. And also this emission reduction factor is inversely proportional to our cost. So here I have the cost over, I would say, overnight cost of clean power system. So this cost is rupees per kilowatt. This is overnight cost of my clean power system. J is my clean power system, N J. Plus I have variable cost. Variable cost of operation and maintenance. Of my clean power system. This is clean power system J. This is again clean power system J. This is also the time is for my clean power system J. This cost is also in rupees per kilowatt hour. So this is variable cost of my clean power system J. So this variable cost of my clean power system J also comes here. So because this is variable cost, this is dependent on time. So the time for which my equipment is operating also comes into play here. So I also have the fixed cost of operation and maintenance of my system J. So this C fixed cost of my, this is fixed cost of operation and maintenance of this clean power system J. This is again in rupees per kilowatt hour. So this cost also needs to have this factor AJ. So this is my emission reduction of the pollutant. This J can be my solar, wind, geothermal, fuel cell, biomass. Any kind of clean energy may be chosen. And how is this related to my local grid? This is explained, or this is considered here in the present model. So this cost benefit analysis can be applied on any emission reduction from the grid electricity consumption in manufacturing by using clean energy supplies. So this quantitative result RI is the amount of emission reduction per unit scale of economic input or investment. So we can see the economic input or investment is on the denominator side. So per unit economic input or the investment is also there, fixed cost is also there. So it must be noted here that the results are the site dependent on the geographical locations due to difference of emission factors of local grid power supply and the actual power output of the clean systems. So it is dependent on site here. So in this section, the application of clean energy supply for conventional manufacturing systems are demonstrated, the reductions are taken into account, and we have discussed various kinds of clean energy resources and how do we even evaluate their efficiency. So I would like to have a break here, and in the next session, that would be a continuation of this session only, we will discuss the renewable energy status in India. Also we will discuss the concept of industrial symbiosis. So let us meet in the next lecture. Thank you.